So this is how physics people model the crystal. Okay, so of course the distance between the actual distance between any two atoms will be in the unit of Armstrong, 10 power minus 10 meter. Okay, it's not even 10 power minus 6 meter micrometer, something that a few hundreds of micrometer can be resolved by human eyes, but this distance cannot be resolved by human eyes. Okay, but we model in a large view and develop physics and understand how things can be used or how things work in solid state physics like that. So let me go to next slide. So basically, I hope you see slide number 6.
Yes, sir.
Okay. Basically, there are 7 different types of crystals, or crystal structures, or crystal system: cubic, tetragonal, orthorhombic, trigonal, hexagonal, monoclinic, and triclinic. Okay, these classifications are made based on the lattice parameters or the lattice constants. Okay, how the ABC and alpha, beta, gamma are related or fixed. Okay, having a fixed value, these classification made. For example, in a cubic case, all the 3 length direction x, y, z direction, you have the length, the difference between 2 successive atoms or the lattice points are same. A, B, C are all equal. A equal to B equal to C to a particular value. And alpha and beta or gamma are all equal, and also they should be 90 degree, not less than that or higher than that. If strictly alpha, beta, gamma are 90 degree and the ABC are the same, that means ABC value are same, equal, and the angle between ABC, any angle between these ABC vectors are 90 degree, then it is called cubic structure. Okay. Next one is if A equal to B but not equal to C, C can be less than A or B, or it can be greater than that, but still the angle alpha, beta, gamma are all equal to 90 degree, then it's called tetragonal structure. Likewise, we can read when I send the slide the way how the things differ. Okay, this is not very important for you, but you have to have a basic knowledge about the crystal structure. Do you see slide number 7? Hello.
Yes, sir.
So next one is primitive cell. Primitive cell means is unit cell. First of all, unit cell is something that is repeating. We saw in the previous slide cubic, tetragonal. Those are different unit cells. Okay, crystal structure. Okay, a unit cell is a unit which repeats upon building. Which repeats to build the entire structure. Just like if you consider the house, you have a block, right? That block is used to build the equally, more or less decently, equal shaped blocks are used to keep one top of the other, one beside the other, and then you build the entire wall for the house. Okay, likewise, these type of blocks, the smallest unit, okay, that is called the unit cell, which when repeats in all 3 directions, it forms the whole crystal. Okay, that's called unit cell. That repeating unit, that smallest repeating unit, if it contains one lattice point as the whole contribution in the unit cell, it is called primitive cell. For example, this is called a simple cubic unit cell. Okay, you have at each corner one lattice point. Okay, you can imagine a sphere at each corner of this cube. Okay, now you can imagine that this corner, you can imagine any corner, maybe let us imagine the bottommost corner, we have one sphere. This sphere is actually shared by how many unit cells? One is drawn here, okay, the other one perpendicular to the screen outward, the other one left side to the screen outward, the other one inside the screen out left side. So likewise 4. So and bottom below that you will have another 4. So totally this each sphere in the corner will be shared by 8 unit cells. Okay, so the actual, perfectly if you calculate, the actual contribution of this one sphere to the one particular unit cell drawn in this picture is actually 1 by 8, because the whole sphere is shared by 8 unit cells. So 1 by 8. So we have 8 corners, 8 spheres. So each corner sphere contributes just 1 by 8 of its volume to this particular unit cell that is drawn. So 1 by 8 times 8, that is equal to 1. So altogether these 8 lattice points contribute only one lattice point or one atom only to this unit cell. So it is called primitive unit cell. Non-primitive unit cell, for example, so this is primitive unit cell is called simple cubic, body-centered cubic. So in addition to what you saw in the previous simple cubic, you have one atom at the center of this body of the cube, okay, at the center of the cube. So you have now 1 plus 1 by 8 into 8, that is 2 atoms in the unit cell. So it is called non-primitive unit cell. Similarly, the other one is called a face-centered cubic. Each plane, you can see each plane, right? If you connect any 4 atoms in the cube, it forms a plane. So in this each plane, you have an atom at the center of the plane. That is called a face-centered cube. So we can call each plane as face. So you have totally 6 faces, okay? 2 faces left side and right side, 2 faces up and down, 2 faces forward and backward, like that. Okay, so you have totally 6 faces, and at the centers of each face you put one atom. So you get face-centered cubic crystal system. Now you have 1 by 8 multiplied by 8 plus 1 by 2 multiplied by 6. So totally 4 atoms, right? So already from the corners we have 1, and from the face center, actually above, if you consider a plane, the topmost plane of the cube, or the top face. So at the center of this we can put one sphere. So what happens? We can place one unit cell above this what is shown in the shown unit cell. So the sphere is actually contributing half of its volume to one unit cell. So each unit cell is actually shared by 2. So each sphere is actually shared by 2 unit cell. So 1 by 2 times 6 faces are there. 6 is the total contribution of atom or lattice points to this face-centered cubic system due to the atoms in the face center. So 1 by 2 times 6 is 3, plus the 8 atoms or 8 lattice points in the corner contributing 1 by 8 times 8, that is 1 unit, lattice point or atom. So totally there are 4 lattice points or 4 atoms, so it's called face-centered cubic. So likewise, so the crystal system, 7 crystal systems are subdivided into multiple types of lattice types: simple cubic, base-centered cubic, face-centered, like that. So those details are not much necessary for yourself. The syllabus is prescribed accordingly to look more on the material aspect and the dwelling the deeper of solid-state physics. The other one is called Wigner-Seith primitive cell. It is something which is not a real cell but an imaginary cell. Okay, so what you got to do is you can consider that's real also, nothing wrong, but real sense it is not used, but mostly used in reciprocal space. Okay, anyway, let's see how we can construct the Wigner-Seith cells. Okay, Wigner-Seith cell is also a primitive cell, which means that cell will have only one lattice point in itself. So you draw, this is a hexagonal lattice. Okay, so you have A and B, okay, as the lattice concerned in 2 dimensions. Third dimension is not existing, only 2 dimensions, A and B. So but in all direction between any 2 lattice points, you draw an intersecting point line. Okay, intersection of line connecting 2 lattice points. Okay, so exactly at the half distance. Okay, then you get this type of lines. So when you extend all these lines connecting each other, it will enclose a volume. That closed volume will have only one lattice point inside. Okay, so that is type of cell is called Wigner-Seith primitive cell. When you draw this in reciprocal space, means 1 by the distance. Okay, the distance between any 2 lattice points is A. Then reciprocal space is an imaginary space. It's not existing in reality. Imagine 1 by A. If 4 angstrom, 1 by 4 angstrom. 1 by 4 angstrom, which means what? 0.25 angstrom inverse, or 0.25 into 10 power 0.25 into 10 power 10 meter inverse. Okay, 0.25 into 10 power 10 meter inverse. So that's what reciprocal space. There is nothing we can imagine. That's imaginary space. Only you can imagine. Okay, so in that imaginary space is called also momentum space. There are a lot of things that are defined about the electronic properties. We will see in detail. So that's why this I introduce as Wigner's primitive cell. Okay. Okay, so it has hexagon symmetry. If the system has hexagon symmetry. Okay, next thing. Do you see slide number 8? Hello, do you see slide number 8?
Yes, sir.
Okay, so this is about defects in crystals. We saw crystals means periodic, regular, perfect arrangement of atoms in space. That's crystal. Okay, that's the ideal definition of crystal, and ideally crystals are supposed to be like that. But practically, most crystals lack of this perfectness. Okay, the periodicity is having some defects with them. Okay. The defects can be simply a point at one particular point in the crystal. There will be defect. Such defects are called point defects, or it can be defect that will be like a line. Okay, such defects are line defects. Okay, likewise. Okay. So, for example, you see, if you assume this is a periodic arrangement of atoms, you see there's a periodic arrangement of atoms. There is perfect arrangement of atoms. The atoms are arranged at equal distance. It is in 2 dimensions it's shown. Okay, but there is one atom that is missing here. Okay, that's called vacancy. It is one of the point defect. That's a missing atom, point defect. Okay, and in the next case, one additional atom exists between 4 atoms. It is supposed to not to be there, but there exists one more additional atom. It is called interstitial atom. Okay, this is also a point defect. Okay, now these point defects can be substitutional also. Okay, for example, here the bottom left side, you have periodic arrangement of atoms. We have all the atoms present, no problem. Compare in the previous case, we were missing one atom, and the next case we saw an additional atom in between 4 atoms where there should not be any atom, but there was one. Here we have all the atoms, nothing is missing, but one atom is actually not of the same of the other atoms. Okay, one atom is different. It is an impurity atom. Okay, for example, if you consider all the open circles representing carbon, okay, the closed circle, the pink color one, is representing some other atom. It's not carbon, something else. So such a type is called substitutional impurity. Okay, or this pink color atom can be at an interstitial position as an additional atom in the perfect crystal system. So it is called interstitial impurities. These are called point defects in crystals. This is how I said earlier. You suppose you have a perfect crystal. For example, quartz supposed to be filled only silicon dioxide, SiO2, only should be making the entire quartz crystal. But sometimes some metal ions, chromium, iron, zinc, maybe occupying some interstitial position or replacing some silicon position. Some few minor, small quantities. 1 in a million, 1 in 10 million, like that. That will change the whole property of the crystal. That's what the importance. Okay. There are millions of atoms making the entire quartz crystal, but we have only some 5-6 chromium atoms in the quartz. Instead of SiO2, we have SiO2 plus millions of SiO2 molecule plus 5 tons of chromium. That will change the color, of appearance. The transparency will be varied. The color of appearance of the quartz crystal will vary. Okay. Likewise, these small inclusions or introduction of foreign atoms, which may be replacing the host atom or occupying some gap in between the host atoms, can change the property of the crystal. These are very important in semiconductor physics as well as superconducting materials and all. So this doping is something called, this can be called doping. You remember doping in crystal, doping semiconductors. These type of things are very important. So introducing foreign atoms can change the property. Next one is dislocation. This is very much important for mechanical engineering. This is a line defect. You can see some additional line of atoms included in the crystal. Okay, it's a three-dimensional picture. You can see one row, one column, two column, three column, four column, five columns of atom. Atomic arrangement is complete. But there is a sixth column that is not starting from top to bottom, but it is stopped at some point. Okay, it is not extended from top to bottom. After three steps, this is terminated. So this is incomplete. This is called line defects. So like this. So this is called dislocations. Dislocations can be moved by hammering the material. So that's why this type of dislocations are very important in metallurgical students or mechanical engineering students when they work with the metals and alloys. Okay, these dislocations can form quite a lot, and they can be moved by forging, heating, and hammering. Okay, these stuffs, and that helps actually make the material to be easily bent without breaking, and also you can hammer them into very thin foil like that. So it's useful in that branches of engineering or science subjects, not for you. And then screw dislocation is another type of dislocation, but not of your importance. Okay, I think I stop here. If you have any quick question for the basics of solid state physics, maybe out of enthusiasm or you could not understand or follow, you can ask the question before getting into the actual topic, Drude's theory of electric conductivity. Any questions, any clarification over the background idea of solid state physics? No questions? Okay, then we can continue. So Drude theory of, do you see slide number 9?
Yes, sir.
Yes, sir.
So Drude theory of electrical conductivity is basically defined or developed for metals. Okay, conductivity of metals. How metals conduct electricity. Of course, the same theory can be developed or extended for heat conduction also. Okay, conductivity of electricity and thermal energy. Okay, so Drude theory of electric conductivity is mainly for metals. Okay, so metals which mean in the solid form. For example, iron is a metal, gold is a metal, it is in the solid form. Okay, so in solid form we consider all metal can be put in liquid form as well as gas form if you melt them. So it's called molten metal otherwise if you heat them. Okay, so we assume solid, as we deal with solid physics, we assume solid form. So if you consider a gold metal, a piece of gold or silver if you want, imagine, then what happens actually, electrons in these, so if you consider gold, the whole metal is containing gold atoms, right? And then if you consider iron, it has iron atom. So we have actually a large number of electrons that are surrounding the core of the atoms, which contains neutrons and protons. So surrounding this nucleus of the atom, there are a large number of electrons. They are arranged following certain quantum mechanical rules in K cell, M cell, L cell, N cell, like that. Okay, so they have a specific arrangement. Okay, the outermost electrons, the electrons are found in the outermost orbital is called the valence electrons. Okay, in metals, the Drude theory assumes these electrons are free. Okay, like whether the set of valence electrons